In this video, we solve problem 8.5.025 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use substitution in partial fractions to find the indefinite integral. And then we're told to remember to use absolute value bars where appropriate, use C, capital C, for the constant of integration. And we have this. Now, I've heard from a couple of students that they're worried about the complexity of this problem. They think that they have to use a Weierstrass substitution in order to evaluate this, and that's not necessary at all. I believe that, it's possible that if you had a computer algebra system solve this problem for you, they might use some kind of substitution that a human looking at this problem probably wouldn't apply. I would recommend that we follow the instructions that are listed up here. So first it says use substitution. So the idea is we're going to do a U substitution. We know how to do U substitutions. And so what we're looking for is some function in this expression to play the role of U, and we want its derivative or a multiple of its derivative to be up here somewhere. We want the derivative times dx. Well, since I have a sine of x dx here, we can think of that as a sine of x multiplying dx. It makes sense to let u equal cosine of x. So if I let u equal cosine of x, and then we compute du, this is what we get. If u is cosine of x, du is the derivative of cosine of x, which is negative sine of x times dx. And now everything up here can be written entirely in terms of u. Now there's not a negative sign or negative sign sign up here. So we will, well, or sine. There's not a negative up here. So we will multiply both sides by a -1 to isolate this sine of x dx. And then we can write this integral entirely in terms of the new variable u. So I think what I'll do is I'll write it like this at first. So we've got 1 over cosine of x plus cosine of x quantity squared times a sine of x dx. I'm just factoring that sine of x off to the right. And then I want to write everything here in terms of u. Well, remember, u is cosine of x. So this can be replaced with a u, and this can be replaced with a u. We are literally writing a u instead of writing cosine of x. So we have a u here, and then we have a u over here. And that works as long as we also substitute this sine of x dx. From this equation, we know that sine of x dx is -1 times du. And you're multiplying by that -1 times du, so it would make sense to factor out that -1. We'll just bring that constant on the outside. Now, if this problem looked complicated, hopefully when you write the problem like this, you think, that's something I can solve because we just learned about partial fraction decomposition. That's why this homework problem is in the partial fraction decomposition section, because after we make the substitution, what we have is a rational function. We've got a polynomial of degree 0 up here and a polynomial of degree 2 in u down here, and that can be factored pretty easily, and then we can rewrite this using partial fraction decomposition. So let's do that. I think I will bring that -1 inside just to make the partial fraction decomposition a little bit simpler. If I factor out a u from each of those terms, I get u times 1 would give me that first u, and then I'll have u times another u would give me that second term. So this denominator factors this way. That means we have two linear factors. Neither factor is repeated. So we can write down the partial fraction decomposition for something that looks like this in this way. We have the original rational expression, and I think I'll put my u before my 1. addition is commutative, so we can add in any order we want. That's fine. And then because these are linear factors that are not repeated, we get a constant over each of those factors in the decomposition. And then we just multiply by the LCD in order to simplify this equation. So before we go any further, I just want to keep outlining the steps for you. We write the integral in terms of u. We recognize it as a partial fraction problem. We factor the denominator as much as possible. And then we write down the appropriate partial fraction decomposition. For that particular rational function. Then to simplify this, we will multiply by the LCD, which is always the original denominator. I know that you can always get a common denominator by multiplying all these guys together, but we want the least common denominator, which will always be the original denominator. So we have u times u plus 1 here. I'm going to multiply every term by u times u plus 1. And then you want to simplify wherever you can. So the u's reduce here, the u plus 1's reduce there, the u's reduce here, and the u plus 1's reduce there. And so what we get is a -1 equals a times u plus 1 plus b times u. Now, if you do that and all the denominators don't cancel and you still have fractions here, you did not choose the correct least common denominator. Or you didn't choose a common denominator. Okay, so we multiply by the LCD and we simplify. And then you have an equation involving your variable u and the two constants a and b that you're trying to solve for. In order to find the value of, or the values of a and b that will satisfy this so that this partial fraction decomposition is actually equal to this, so that this expression is equal to that expression, we just choose values for u that cause each of these factors to be 0. Then when we do that, we substitute those into the equation and solve for a and b. So u plus 1 would equal 0 if u was -1. So let's let u equal -1. When u equals -1, the left-hand side is still -1. And then we'll have a times -1 plus 1, which is 0, plus b times -1. So -1 equals -b. So multiplying both sides by -1, we get b equals +1. And then to cause this factor to be 0, we just let u equal 0. If u equals 0, the left-hand side is -1, and then we have a times 0 plus 1, so that's just a, plus b times 0. Of course, b times 0 is 0, and so now we know that a is equal to -1. All right, so this expression right here can be rewritten this way, where a equals -1 and b equals 1. So we have a -1 over u plus 1 over u plus 1. Going back to the original integral. We have that right there. Now this first one we have a basic rule for. We just get -1 times the natural log of the absolute value of u plus this integral. Now with that integral, we need a u substitution, but we've already used u for something else. So maybe we'll use a w, call it a w substitution. W is equal to this denominator, then dW is just 1 times du. So then this will become a 1 over W times dW. So we have negative natural log of the absolute value of u plus the integral of 1 over W dW. And the integral of 1 over W dW is just another natural log. So we get this, negative natural log of the absolute value of u plus 1 over, the antiderivative of 1 over W, which is the positive natural log of the absolute value of W plus C. But now we've got to back substitute. Remember, W is actually u plus 1, so we need to substitute that in. And then from here, we have to remember what u is. Remember, u is cosine of x. We started with that at the very beginning. Okay, so we're back substituting W equals u plus 1 here, and then we're back substituting u equals cosine of x. And this would be fine for me for an exam, and I believe WebAssign would accept that as an answer. That's the answer that I would expect you to give if you were submitting this answer on an exam. But if you are checking your answer against an answer in the back of the book, they may simplify this a little bit. A couple of things that they may do to simplify are using log properties and then using trigonometric identities. So we know that log of A minus log of B is the log of A over B. Well, with that in mind, since this is a positive logarithm and I'm subtracting that logarithm, or I have a negative logarithm there, I could rewrite this in this order. And then this would be my A, and then this would be my B. So using this property here, we'd have natural log of A over B. So that's an alternate form of the answer. But since we have a single expression in this denominator, we could split this up even further. If you know that if you have 1/3 and then you're adding 4/3, you keep the common denominator and just add the numerators. You'd have 5 here. In general, that's true. If you have A over C plus B over C, keep the common denominator and then you just add the A and B. Well, that goes backwards as well. So if you have a sum up here, you can just call that A over C plus B over C. You can, instead of going this way, we could go this way. So we could take each of these terms and divide by cosine of x, and that would be totally fine. And then we would simplify. The cosine of x over cosine of x is 1, and 1 over cosine of x is secant of x. That's from trig. 1 over cosine of some angle is secant of that angle. Now, chances are that this is the answer in the back of the book in the Larson textbook. But this would be fine, and this would be fine. And this is what I would expect you to do if you were just, or expect you to get if you're just following these directions. Use the substitution. So we're going to let u equal whatever is appropriate so that we can write the integral in terms of u. In this case, since there's a sine of x up here, we let u equal cosine of x. Then we get here, we use partial fractions, and then we use partial fractions to solve the problem. That gets us right here. But with a little bit of algebra and a little bit of trig, we could write our answer in this way as well. Okay, so let's just go over the method. I think I left off a few steps as we were going through it. So they ask us to use substitution. We choose u equals cosine of x, and then we compute du. We solve for sine of x dx because that's what we have in our integrand. And then we write everything up there in terms of u. So that gets us here. And then we say, look, I've got a rational function in u, so let's factor that denominator completely and use partial fraction decomposition. So we state the partial fraction decomposition. We multiply by the LCD to clear the fractions. And then we choose values of u to cause each factor to be 0. And that gives us values of a and b. And then once you have a and b, you substitute those into the partial fraction decomposition. And then you antidifferentiate. Now the first one was a basic rule. The second one required another substitution, but then it was a basic rule. And then we back substituted twice. W was u plus 1 and u was cosine of x, and that got us here. And then of course you could do the algebra and trig to get any one of these other answers.